Okay, so we're going to prove now that in a parallelogram that that the diagonals bisect each other. So let's see what that means. Let's kind of think about this for a minute. Here would be one diagonal, right? And here is the other diagonal. Now, just so that you know, diagonal doesn't just mean the direction that an angle, a segment is going, and I know sometimes kids think of it that way, that, you know, a diagonal goes kind of sideways and up, you know, kind of in a diagonal direction. We use it as a directional term. But in geometry, we know this also is going in a diagonal direction, right? And it's not a diagonal, it's a side. So when we use the term diagonal in geometry, we're talking about a segment that connects two vertices inside of a polygon, okay? But they are non-adjacent vertices, so they're going to skip at least one, okay? So diagonal goes from this vertex. It cannot be a diagonal if it goes to the adjacent, because that would make it a side, right? Segment goes from one vertex to the adjacent vertex, not going to be a diagonal, it's going to be a side. But when it skips one, it becomes a diagonal. Okay, so we have two diagonals here, and you know what it says is that somehow these guys bisect each other. Well, we're going to verify that real quick. We'll get the intersection point of the diagonals. I think I'm actually going to take these lines off now, and we'll just build segments out. Okay, so we can see, you know, the idea is that each of these segments, if they're bisected, then this segment will measure the same as that segment, etc. And we can look over here and we can already see that if we highlight one diagonal, it's 2.7. We highlight the other diagonal, it's also 2.7. So it's already measured for us on the algebra side over here, 4.17, 4.17. So it's confirmed already, but I'm going to do a little bit more just because I want to change my parallelogram just a teeny bit. Okay, so I've got my measurements there. You can see that it does bisect, but now if I modify, we grab my, wait a minute, what is going on here? Sorry, I change, see, can I change that? Can I change? Why am I not able to grab a point? Well, I don't know. I'm having troubles here. So I was gonna. Oh, there we go. Okay. So now as I change my polygon or my parallelogram, it's still a parallelogram. I constructed it so it'd always be a parallelogram. But you can see that wherever I stop, the measurements of those diagonals remains the same. I should be able to do that for each of these. I don't know why it's wanting me to. I gotta make sure I'm grabbing the point and not the segment. Okay, but you can see that that is true, that the diagonals are bisecting each other in every case. So now the question is, why is that? Why do they bisect each other? And can we prove that for any, without taking a measurement, just logically, can we prove that for any parallelogram that the diagonals are going to bisect each other? Now, this is really actually not a hard proof. Especially if we've made it this far, we already understand a bit about parallelograms. So what we do know is that this angle here, since the sides are parallel, this segment that goes from C to B actually is a transversal of these two lines, line CD and line AB, and we see only the segment, right? Segment CD and segment AB, which are parallel, and CB is a transversal of that. And so we have alternate interior angles for this angle DCB and angle ABC. Okay, so these two angles are going to be congruent because that is they are alternate interior angles at a transversal of parallel lines. And of course, that means that we can use the same logic here for these two angles because they are also alternate interiors from this transversal of these parallel lines. So we have two angles that are congruent, and then we've already proven that opposite sides are congruent. So now we have something that we call angle side angle. And what angle side angle simply means is it just means that if we were to consider this as a triangle, it's just another way of saying that this triangle formed right here. Okay, and I'll make a copy of that real quick. Well, let me hit escape real quick, make sure I don't have anything selected. Let's try that again. So that this triangle, which is right there, okay, that triangle is going to be congruent to the other triangle, which matches angle, side, and angle. So we're looking inside of these triangles. Here we go. We're going to make the second triangle here. And then we will make sure we have everything cleared out. Use my rigid tool and select this triangle here. I have two I have two triangles now. Alright, those are the two triangles that we're talking about. Okay, and they are congruent to each other by angle, side, angle, which means anytime you have two triangles where you have two angles and the side in between them, they must be congruent. Now, once we've proven that, then we know that the corresponding parts, right, of congruent triangles must themselves be congruent. CPCTC. So I'm going to use 3 here to show that it's a little different than this one, but than the others, but it's the same here, right? So here we go. Let's type out our little proof the way we would want it to read. We'd say something like this. You know, figure ABCD, is a parallelogram, and that is given, right? That was given to us, and so then we know that we can just say side AB is parallel to side CD. That is the definition of a parallelogram. Okay, and then angle DCB and we gotta put the word angle DCB and angle let's see, ABC are alt interiors and therefore congruent. Alright, and we'll do the other one. Let's see, we go angle angle ADC and angle ADC and then CBA are alt interiors and therefore congruent as well. And we also have the sides because, okay, so we have side CDC is congruent to AB, and because our opposite sides a parallelogram. Okay, and so therefore by angle side angle triangle, let's see, what did we call it, DCE is congruent to triangle, let's see, ABE. Okay, so that's by angle side angle, and by CPCTC, comma AE, which is the corresponding part to DE, and they are congruent, and by the same logic, BE and CE are congruent. Okay, let's just kind of talk that one real quick. Here we go. Boy, I hope you can see. If I place park that where you can kind of read that okay. Maybe that's the best we're going to get. Okay, ABCD is a parallelogram that was given to us. So we know that AB, right here, is parallel to CD, and that is the definition of a parallelogram. Angle A or DCB, so DCB, this angle here, is congruent to angle ABC right there because they are alternate interiors of parallel sides and therefore congruent. And ADC and CBA, so ADC, that's this one right here, and CB, no, that's not right, is it? ADC, that's this one here, and angle CBA, yeah, it's not CBA. It's got to be changed. That's got to be DAB. This one should be DAB. Let's see if I can update this. How do I update this? Let's see. Cancel. Can I update it? No. I should be able to edit this text. Oh boy, I've got an error in here. It's not CBA. So I better get my pen tool and we're going to cross out CBA because that's a mistake. And I'm going to maybe just draw very small. Hopefully I don't screw everything up here. Okay, so it's angle ADC, that's this one, is congruent to DAB. So it's angle DAB. Okay? So those two are congruent because they are alternate interiors angles of a transversal of parallel lines, right? That's the key part. And then DC, right here, is congruent to AB because they are opposite sides of a parallelogram. And by angle, side angle, this triangle, right, is congruent to the other triangle by CPCTC. So corresponding parts, congruent triangles are congruent. This side matches that one, and this side matches that one. They're congruent, okay? So that's the idea there.